Okay, guys, this video is about lab number 2, Newton's second law, and I'm going to do my best to help guide you, and hopefully this video won't be very long. So, what do I have? I actually have 6 graphs. I got as far as you guys did. This is the for part 2, total mass and the relationship to acceleration. And it is nonlinear. So this is like your original graph for part 2, and we can kind of see, well, it's a little bit nonlinear, and it's also a negative slope, and that by itself is not something that's going to help us out tremendously. So what I've done is I tried to go through the whole linearization process. I said, well, what if the total mass was total mass squared? And it sort of actually doesn't look much different, right? Still kind of sort of maybe linear, maybe not, but still a negative slope. Okay, down here I've got total mass raised to the 1/2 power, so that's like the square root of the total mass, and still negative, but it's even curvier. So what I'm going to do is I'm going to discount these guys. I'm looking for a graph that looks linear with a positive slope to it. These all have negative slopes, and so I'm going to get rid of these guys and not count them, not consider them. Here I've got acceleration as affected by the inverse of total mass, so total mass to the -1 power. And it's got the right slope to it. Here I've got acceleration as affected by the square of the inverse of the total mass. So what does that really mean right there? So this is like 1 over total mass. This is like 1 over the square of total mass. Okay, so which is more linear and which is less linear? Well, that sort of doesn't look linear, and that sort of looks less linear, roughly eyeballing things. That got a little worse. How about this last one? Total mass raised to the -1/2 power. So essentially this is 1 over, hope you can see that, total mass to the 1/2 power, which is like the square root of the total mass. All right, so what's the deal here? Oh, that actually looks like the best one, and that's terrible. So we're actually supposed to be seeing this one work the best. This one's supposed to give us the best linear relationship. I'm actually not sure why, I'm not positive why this one is not giving us the best relationship. I have an idea. So think about this. If you recall, I'll come back to this graph in a minute. If you recall our setup, we had this cart, and pulley, and hanging mass. And what we did was we said, you know, for part 2, we're changing the total mass, and so that value is changing, that we increase that. So the more we loaded into the cart, the less acceleration we saw. Going back to our original, that makes some sense. Total mass, the larger the total mass, the lower the acceleration. Okay. But what else is going on with the blue cart? Well, with that blue cart, the more mass we loaded into this guy, you know, we threw something in there, we kept loading this thing up. What do you think is happening to the wheels and the axles and the friction right in there? The friction is going to be increasing. This is something we're going to be learning about in this unit as well. And if there's more friction here at those wheels, then that pull right there, which was a constant value, that was unchanged, right? That pull would be more and more canceled by some of this friction. We would probably see less and less acceleration. Now, I can't verify this with numbers quantitatively, but what I can do is with some conjecture, I can say, look, the more mass we had, the less acceleration. So flip this around, or take the inverse of the total mass. then the more total mass, then the smaller the value of this fraction. That means we would get more acceleration. And so if I look at this, the first three dots, first three data points, rather linear. Now, I can't trust that. It's not really enough data. But what if you get enough mass in here to start affecting things? Actually, it would be the last three data points that are also kind of linear if we just look at that. But that's kind of a lesson in how many data points you really need to see a trend. But what am I talking about here? I'm talking about the value of this total mass increasing, which means the value of the entire fraction decreases. So as the denominator increases, the overall value decreases. Okay. And with larger total mass, I'm supposing, I'm sort of conjecturing, larger total mass, we actually saw less acceleration because there's more friction here. That actually ended up reducing the net force overall. This was pulling down with the same amount, but we were pulling against some friction here that was increasing. And so with larger total mass, we got a lower value of this fraction, so lower values here. Well, what did we see? We saw the drop-off of the accelerations. If you kind of imagine that line and look where these dots are, they're below that line. There's a, let me get a light color going here. Hopefully this is going to be a light color. Okay, look, oh, that one is going to go away. Okay. I don't know if you saw that. That was kind of amazing. That one and then that one. They're significantly lower below that line. The acceleration is lower than expected here. So what's going on? Really, this kind of graph is supposed to produce a linear result. Okay, so what does that mean for us? I'm going to grab that pen before it starts marking everything up. Hang on with me. Okay. What does that mean for us? So what we see in part one of this lab is that acceleration is directly proportional to the net force. The larger the net force, the greater acceleration we get. We see that because we have this linear relationship in the graph. Acceleration, net force. What about part two? In part two, we see that acceleration is directly proportional to. Now, kind of fudging a little bit, right? I'm telling you, this is the one we should get. And this can even be explained. The fact that it's not linear, I'm conjecturing, can be explained. And when I'm doing that, you can actually include that in your lab report if you like. The reason this is not linear is likely because of the extra friction reducing the net force. Now, we're not reducing this downward pull, but more friction in those wheels is canceling out more of that downward pull. And that results in a lower acceleration for us, lower than expected. All right, maybe I got to get some new blue cards. Anyway, back to this business. In part two, the acceleration was directly proportional to the inverse of the total mass, 1 over the total mass. And so we see that from what should be a linear graph here versus to the -1 power. And so here's the significance of this. What we're looking for in parts 1 and part 2 are these results, but we want to end up at a mathematical relationship between the three of them, between acceleration, net force, and total mass. And so we simply combine our results. What we end up with is, since acceleration is proportional to net force and acceleration is proportional to 1 over total mass, then putting those together, it's not unreasonable to say, well, what if there is this equation, this combination that gives us a true mathematical equation? And it turns out that's it. It's a really simple relationship. The acceleration of a system is directly proportional to the net force acting on the system and inversely proportional to the total mass of that system. And that, ladies and gentlemen, is Newton's second law. And you may have already seen it. In fact, you may see it written more commonly as net force equals mass times acceleration. But initially, Newton would have expressed it this way instead. Not that it matters. You know, it's the same equation, same formula. However, we're talking about the acceleration that a system experiences depends on those two things right there. It isn't the net force depends on the mass. No, not at all. And the net force certainly doesn't depend on the acceleration. It's kind of the other way around. There it is. That's where you want to get with this lab. You're going to want to pick this graph, this way of treating total mass, and you're expecting to see a linear graph. We do not see a linear graph. These accelerations down here are lower than expected. That can probably be explained by friction in the wheels, increased friction due to the mass we were adding here. And the increased friction canceled more of this downward pull, more of the tension in the rope, accelerating things this way. And therefore, we actually had two things happening. We increased the total mass of the system, and at the same time ended up decreasing the net force acting on the system. And that's unfortunate for us, but that's what we have to deal with. But that's likely why we don't see linear here. And when you get parts 1 and parts 2 together, you get Newton's second law of motion. There it is. So I want you to take this, and please email me when you have questions, if you want some advice, if something is unclear. And hopefully this helps, and I will talk to you guys soon. Bye-bye.